Welcome, everybody. Today we have the pleasure to have Jiayuan. She's a research scientist at Amazon Pharm and an incoming assistant professor at the University of Pennsylvania. She finished her PhD at MIT, advised by Professor Josh Tenenbaum and Leslie Kelblin. Her research agenda is to build machines that can continuously learn concepts, for example, properties, relations, rules, and skills, from their experience and apply them for reasoning and planning in the physical world. Her research topics include visual reasoning, robotics manipulation, scene and activity understanding, and language acquisition. She was named a Rising Star in EECS 2024 and in Generative AI 2024 as well. Her research has received Best Papers Award at CogSci 2024, so-called NLP 2024, and Coral 2024 in the workshop of Language and Robot Learning, as well as the Best Paper nomination at ACL 2019. Again, we're thrilled to have you. Jiayuan, the floor is yours. Take it away.
All right, yeah, thanks for having me. So just want to check, can everyone see my share screen?
Yeah, we can see it.
Okay, good. So yeah, nice to meet everyone. So my name is Jiayuan. I'm currently a research scientist at Amazon Pharm, which stands for Frontier for AI and Robotics, and I'm gonna be an incoming professor at the University of Pennsylvania next year. So the theme of today's talk is gonna be learning, reasoning, and planning with neuro-symbolic concepts. So to start with, I'm going to ask this general question, how to build a general purpose physical intelligence. That is, something that can perceive the thing, understand human intentions, make plans and execute them in the physical world. One of the approach that have been currently pursued by a lot of the industrial companies, on the West Coast, is building some policy pie, that maps from observations to actions. And then you think about intelligence as fitting functions to some data sets. So in order to have certain kind of intelligence, you just collect some kind of data sets. So for example, this is a video released earlier this year from a company called Physical Intelligence on the West Coast. And what they're doing is they're training their robot to fold a box. And what they're doing is they're collecting a bunch of human demonstrations of how to fold this box. And they train their system on predicting the action. If you look at some of the the technical spec of it, you find that it's actually not very satisfactory. For example, they need 100 hours of training data just for this particular kinds of bugs on a very similar table. And if you test their in-distribution success, that is, for the same model of box, you get some success rate like 0.6. I want to contrast this with what a human can do. Humans can learn from one example and generalize reliably to all sorts of different states and novel goals. Actually, let me try to optimize for video sharing because I'm going to play some videos now. So look at this video. Someone is showing you, how to cut a bottle into a funnel and use that to pour some liquids. So immediately after seeing this video, you can, apply the same skill to different kinds of bottle with different kind of tool for different kind of liquids. So here's another thing that shows, the diversity of the task that a human can do. When you're in a novel house, and if someone gives you some instructions about how to clean a house, you would definitely see, novel objects you have never seen before. Some kind of targeted configuration of the thing you've never encountered before, but you can still generalize to that. Here's a very simple physical game that really emphasizes what kind of generalization or how remarkable human generalization can be. So the task is called ABC pickup. The rule is simple. You have a bunch of objects on a table, and you're going to pick two of them. Let's call them A and B, and you're going to hold them one with each hand. And then the task is to pick a third object C on the table and try to lift it up from the table. So in this case, the player is trying to, hold up hand and hold up cap and trying to lift up a glass from the table. So this is probably some task you've never seen before ever in your life. And in particular, this particular combination of using a pen and a cap to pick up a glass. But, you can still, make some plan, make some reasonable guess about how you can potentially do that. And, try to execute that and then, try to adapt also like that. So a natural question to ask is, will scaling up just help? So can we just, scale up the data we have and then hopefully we can get at a level of, generalization? So this is a very tough question to answer, but we do have some evidences from the scaling law from complexity theory. So in NURBS 2023, I proved this theory saying For transformer policies, its size needs to scale exponentially with the number of subgoals that cannot be achieved independently. So to break down this theory, what I mean is, suppose that you want to build a policy for a particular task. You can try to decompose that into 3 different subgoals, let's say, subgoal 1, 2, and 3. And you can train separate policies, pi 1, pi 2, and pi 3, to accomplish each one of them. If the original task can be solved by decomposing them into 3 different subgoals and solving them independently, and then just concatenating together or stitching the policy together, then there is a small policy for the original task. In other words, if such kind of decomposition exists, then the original task is simple. However, if not, you need to increase the size of your transformer exponentially. So to further ground this onto the ABC pickup game we just saw, it's very attractive to break down the original task into 3 subgoals. Let's say pickup A, pickup B, and pickup C. But you will realize that this kind of decomposition actually doesn't work. The reason is that the way that you pick up A or the way that you pick up B would kind of affect whether or how you can pick up C. That is, when you're making a decision about how to pick up A and B, you need to consider later on how do you want to pick up C. So you cannot do this kind of decomposition. This means that this particular task is actually hard. So for people who are familiar with complexity theory, such kind of exponential results is not like very surprising to you probably, because fundamentally a lot of problems they're NP hard or P space hard. But what we're showing in this paper is a connection between fine-grained complexity. That is, we can define the complexity of a task by measuring what's the number of dependent subgoals inside it, and connect that to neural network size, and also shed some light on what amount of data or how easy it is to train such kind of neural network. So based on all those observations, so in today's talk, I'm going to focus on introducing a different kind of paradigm I will call a new paradigm for building AI that can learn from one example or very few examples and can generalize out of distribution by combining all the machine learning tools we have and also the reasoning tools that we have built, like the algorithm, the representations, to have such kind of generalizable AI. So all of this starts with thinking about intelligence as world modeling and test time planning. So think about the physical decision-making task. Suppose that you're in a kitchen and then you have some goal, like I want to clean the plate. As humans, we can build a tree search algorithm to do that, leveraging a transition model. That is, you have some representation about the initial state. You think about, what are the possible actions to take in the first state, which gives you, some prediction about what will happen after taking those actions. And you can do that recursively, enumerating sequences of actions. And finally find a plan, to solve the particular task. Such kind of tree search with some transition model, either learned or human programmed, is definitely not new in AI. Actually, a lot of the recent success in AI, including AlphaGo, AlphaGeometry, or even to some sense, channel sort reasoning, is doing certain kinds of test time computation. Here, there is an implicit assumption I want to mention, which is the transition model here, like predicting what will happen if you take an action. We hypothesize or we assume those things are more compact to be learned than the policy itself. So we decided to learn the transition model and using a tree search algorithm at test time, to solve the task. This brings us to the next question, which is, what kind of world model should we build? Of course, we can try to build just end-to-end world model, for example, doing some pixel level prediction. This is what exactly, video generated model is doing. And this is a video generated by OpenAI Sora. I collected this video like maybe 6 months ago, but so maybe right now it got slightly improved, but I think all the points I want to mention still hold. So I'm prompting it to generate a video of, the robot, trying to clean a plate under running water. And you can see that, the generated video is completely physically infeasible. And if you have such kind of video, there's no way you can actually make plans or execute actions in the physical world to do that. So here the challenge becomes, how would this idea scale? Like, can we just scale this approach? And actually also, suppose that we can have such kind of video prediction model as our word model. How can we efficiently plan with it? So in today's talk, I'm going to focus on a different kind of word model and inference algorithm that is focusing on the idea of learning an abstract and compositional word model. So again, think about the kitchen sink example. As humans, we can recognize there are different objects inside the sink, including the robots and different kinds of objects, and they have different states. Like, robot have joints, the object have shapes, poses and dirtiness degrees, and so on. For actions, you can think about them operate on all those factors describing object states, and they will change certain aspects of the state, such as you will change the robot joints, and then you will change the pose of it, but will keep the shape of the plate unchanged. And here the idea is we're going to learn and compose such kind of concepts. What do I mean by concepts here is, those object states and also actions, to do the reasoning and planning to solve physical intelligence tasks. So today I'm going to introduce this idea of neuro-symbolic concepts. So it is a representation that really connects vision, language, and action. And then for now, you can think about it as some compositional abstractions of states and actions. And then it really bridges, vision, language, and action, but does not live in just one single modality. With the goal of building system that can learn from one example and generalize out of distribution. So to do that, I'm going to start with part one, which is I'm going to introduce you what do I exactly mean by neuro-symbolic concepts, focusing on an example in visual language understanding task. And then soon after that, I'm going to move on to actions, including part two, how we can do one-shot learning of generalizable actions by bridging vision and action representations. And later on, learning to do long horizon planning, like solving the kitchen cleaning task by bridging vision, action, and language. So with all that, let's jump into the first part. So neuro-symbolic concepts, they form a compositional and abstract word model. So at the the mathematical level, you can think about it as have two parts. The first part is what we call state features, and the second one is action models. So here features are some feature ID, and it takes some arguments which are entities in the physical world, and usually they're associated with some extractors that can compute those feature value from raw observations. So usually those extractors are implemented by neural networks. So you can also have relational features, talking about, for example, having a neural network predicting what's the relative pose between two entities in the world. You can have actions. I'm going to use a particular representation for actions, including its preconditions. That is, certain aspects of the scene must be true before you can take an action. The body of it, so that is how to actually drive your robot to do the task. And some effect prediction model, that is, predict what will happen, how this action will change the states of the world. So again, this idea of building state features and action models and use them for reasoning and planning is not completely new. Actually, in the past, in old AI era, we have tried a lot of ways to do that. But we saw some bad practices. For example, we saw, okay, so if you want to build a fully discrete representation of the world, it's really gonna fail. And also, you should not heavily rely on human-defined models, or you want to train those models from dense supervision, because those kind of approach won't really scale. So in today's talk, I'm going to focus on the idea of learning such kind of neuro-symbolic concept from language. So to do that, we're going to start with defining all those entities, being physical primitives, such as objects or physical events or robot commands. And for those names of those features and actions, and then way how they relate to each other, like this state feature is a precondition for another action, they're going to be obtained from language. And here, the key insight we're going to explore again and again in today's talk is going to use those language symbols to define the overall structure, such as how to factorize the state representation of the world and how to have the sparsity structure in your action transition model, and leverage learning with minimal human priors and without dense supervision to learn how to recognize features and how to perform actions. So all of this is a little bit like an abstract, but I'm going to soon describe a concrete example of this in the context of visual question answering. So here the task is, given an image and given a sentence and like a query, and I want to ask, want to answer, what's the answer to this question? And then, first of all, I want to mention, first of all, this is relatively old work. This is like published 6 years ago in iClear. And, this is also not like a robotic focus. So I'm gonna, do it relatively quickly. But the reason I'm mentioning this work here in this robotic seminar is because this kind of, this particular demonstration illustrates what are the key insights and what are the key learning algorithms for neuro-symbolic concepts. And then later on in robotics concept, we're gonna leverage, the approaches and the representation we built here again. So going back to the visual question answering task. So, the typical way to solve such kind of task is say, we are going to train an end-to-end neural network, such as a transformer. And then we're going to train it to predict the answer to the original question. Is the plate on the counter? And the answer is yes. So if you think about the learning of this end-to-end neural network, there are two things to be learned. The first one is what we call concepts. That is, how to recognize object shapes and relationships. And the second one is the capability to do reasoning, including, how to count objects or, how to, check if there are a particular combination of object pairs exist in the world. So then the limitation becomes, really, you want to train such kind of thing to do many tasks like concept learning and reasoning. You need a large scale data set. And also after learning, the learned neural network will not transfer very well to other tasks. Our idea is to disentangle concept learning and reasoning. So it starts with thinking about a query, representing that as a little program, but resembles the original reasoning structure of the question. For example, in this case, the query is there a plate on the counter? We're going to translate that into a three-step program. The first step is we're going to find an object that is a counter using like a primitive filter operation. And the second one is we're going to find an object X, such that X is on Y and X is a plate. And finally, we want to check, if such kind of object exists or not. So this particular task is called, language parsing or semantic parsing, or, you can think about it just like, language to code generation. And this is, typically recently they are done by large language models and is a relatively well solved task. So this is not the focus of today's talk. We're going to assume that this step is already done for us. So we can have a visual illustration of the program structure. It has 3 steps: filter Y, filter X, and counting the number of objects. And there are a bunch of concepts being mentioned here in this little program. However, it's important to mention that even though you can have some model predicting a program in some like text space, but the concepts being mentioned here, like counter or plate or on, they are completely uninterpreted to the neural network or to the robot, because I don't even know what is meant by a counter. So here what we need to do is you want to learn how to recognize counter and how to recognize plate and how to recognize the relationship on. The way that we do that is we do a differentiable execution on of the program based on the scene representation. So it starts with doing general purpose object detection, by segmenting the original scene into a bunch of object masks. And recall that counter here is a neural network, is associated with a neural network that maps from the object representation, like the mask and the RGB pixels, to a value that classifies whether an object being a counter or not. So you can apply, this neural network on each individual objects, and you will get a score distribution indicating which object is likely to be the counter. And you can compose that result with the relationship on classifier, trying to get a set of objects where the object is on the counter. So you can compute this probability in this way, such as the probability that X is on the counter equals to the probability of some summation that Y is a counter and X is on top of Y. And you can do the similar thing for recognizing where is the plate. You can do a similar trick of composing those probability distributions to compute the conjunction of 2 sets. And then finally, make predictions about what's the likelihood, what's the probability that the set is not empty. So in this execution, basically we're composing the probabilistic output of each individual neural network for doing the recognition task for us. And composing the probability following the program structure in a principled way. Like, for conjunction, we're taking the product, and for disjunction, can do some other kind of operations. The advantage of this kind of computation is the final answer is going to be differentiable with respect to all the intermediate answers, and also subsequently to all the neural network weights. That is, the entire computation graph constructed in this way is actually end-to-end differentiable. Therefore, if you have, the original answer to the original question, then you can just use that as the supervision and use very standard backpropagation algorithm to supervise the learning of how to recognize counter, how to recognize the relationship on. So in this framework, what we're doing is we're extracting all the concepts by parsing questions. So basically just need a data set of questions and you ask like a semantic parser to parse it. You don't have to manually annotate. Here is the set of concepts you need to learn. And second of all, you don't need to have fine-grained labels like this object is a counter, these two objects have the relationship on. Instead, you just need paired question and answer data, and then of course some images, questions and answers. And then all those concepts can be trained from such kind of paired QA data, without fine-grained annotations. So for this part, I've described a framework for doing such kind of learning concepts from images and languages. And the advantage of the system includes strong data efficiency. And in the paper, we show that it's really 10 times, more than 10 times more efficient than their neural network counterparts. And the learned representation, such as individual concepts, the recognition networks, they can transfer to different tasks. You can use them for retrieval, you can use them for counting, you can then use them for robotic planning purposes. And then the principle here is we leverage language to help us disentangle concept learning and reasoning. And so this is an idea that is quite general, does not only apply to image understanding. Originally, it has been applied to 2D question answering case, and later on, a lot of the follow-up work has followed my previous work, extending this to physical reasoning domains, like reasoning about causal relationship between events in a video, or to 3D scene understanding, like understanding point clouds or scene scans. And also, to temporal sequence modeling, such as, understanding human motion capture and answering questions about it. So in NeurIPS 2023, we described this extended, the original idea into a more general framework that combines large language model for their language understanding capability, like parsing the sentence into programs and extract all the concepts being mentioned in that question, and the concept learning framework we have to build systems that can learn from very few examples and do reasoning across all different kind of domains, 2D, 3D, videos, and motion capture, or temporal data, all those kind of things. And of course, such kind of representations and algorithms will be very useful for a lot of other applications, especially those applications where the data is scarce or where interpretability or generalizability is very important. So here's like a very brief overview of like what do I mean by neuro-symbolic concept grounded in a visual question answering case. So since this is a robotics focused seminar, of course, next I'm going to move on to how we think about actions. So I'm going to first talk about, how should we represent an action as in a neuro-symbolic way. Previously, we talked about, okay, so an action representation has three parts. It has a precondition, it has a body, it has some effects. Here, the preconditions and effects, they're basically defined on state features. But a question we haven't really addressed yet is, how should we represent the body of an action? So an attractive, easy way to do is, we represent them as a policy, like a sensory motor controller, some neural networks. However, there is an issue with it, which we already mentioned at the very beginning of the talk, which is such kind of policy representation for actions are not very composable. So if you think about the ABC pickup game, suppose that you have, three policies, one for pick up the pen, the other one for pick up the cap, the third one for pivot the glass. They cannot be directly stitched together to solve the original task of, using pen and cap to pivot the glass from the table. So today I'm going to focus on thinking about action generation as solving a constraint optimization framework. So think about the simple skill of pickup. Our goal here is really generate a trajectory of the robot that satisfies, first of all, some past constraints, like I want to stay within my joint limits. I want to avoid collision with other objects in the world, and with the goal of holding the target at the end. So this representation will allow you to compose multiple actions. For example, right now, if you want to find a trajectory to, or find a trajectory to, pick up the plate from the table, from the counter, and place it onto the dish rack, you need to do is you want to generate a trajectory which has two segments and satisfying all the past constraints, having the first sub-goal being holding the target, having the second sub-goal being played on the rock. And this thing can be formalized as a constraint optimization problem, which given the original state as 0, you want to find two trajectories, T1 and T2, and two subsequent sub-goal states, minimize some cost, like total length of your trajectories, subject to first of all the physical dynamics. Executing T1 starting from S0 give you S1, executing T2 from S1 give you S2. Having some collision-free constraints over your paths. Want to hold the target as S1. Want to continue holding the target throughout the T2, and having the target on the rack in S2. So all those constraints can be categorized, into, you have some parts is about physical dynamics. In this case, just really rigid body physics. You have some geometric constraints, like, want to avoid collision. And also you have more task relevant constraints, like I want to code in the target, I want to have the target on the rack. So think about action generation as a constraint optimization framework, give you two leverages. The first one is now learning can happen at two levels. The first one is the set of constraints to satisfy if you want to accomplish a task. And the second one is how to generate values that satisfy individual constraints, like how to generate a collision-free path. Second of all, it also allows you to build out human-built physics models. What I mean by that is, if you know the targeted domain only requires you to reason about rigid body physics, you can just directly rely on physical simulator to predict what will happen if you perform a particular action. And you can use motion planner to solve the geometric constraints, like finding collision-free paths. And only for those task-relevant constraints and you do not have human-built models for, you can leverage learning to help you. So I'm going to do a case study on learning to hand objects from one single example. That is, you are seeing some, robot demonstration as a reference demonstration of someone controlling the robot trying to hand a hanger onto a rod. And I want to generalize this to novel things with novel objects and novel goals, like, hand this mug onto the mug tree. And the challenge here is recall that there is all those joint constraints among where to grasp and where to hang, and what is the robot motion to avoid collision with all different kind of objects in the environment. So in the past, a lot of our approaches have been proposed to solve such kind of task. The first one is completely model-based planning. You reconstruct all the 3D shapes of objects and you try to find a plan for grasping, for hanging, and then use physical simulator to test everything. Usually this is very, very slow. People have also explored ideas of doing unsupervised learning and policy learning. Basically, the high-level recipe is you're pre-training some neural network representation on a bunch of mugs. Usually they're synthetically generated. In this case, they generated like 100,000 synthetic mugs. And you're fine-tune, based on that representation, you're fine-tune a policy using very few examples. And here, the performance is something like one-shot generalization performance 42% to mugs you have never seen before. And then, later on that, you want to generalize this to a novel object category that I have never seen before. So what we do is we're building our learning algorithm that learns, first of all, what is the set of constraints to satisfy along the trajectory. This boils down to learning the sequence of contacts being made between objects throughout the entire trajectory. Like at the very beginning, you want to pick up the object to be hang, and then second of all, you want to make a contact between the hang and also the target object to hang onto. And the second of all is how you can generate values. And then we are going to leverage visual pre-trained models for one-shot transfer purposes. So in this particular case, what we're doing is doing a constraint optimization with visual guidance. So what we do is we look at the input video, like the one-shot demonstration. We extract all the contacts happened in that video or in that demonstration. And then here, a contact is basically a point on the object mask. And then at test time, we have an image. In this case, we're just using the image first of the target object to hang onto. We can use a visual pre-trained model. In our particular case, we use the Dino V2 to compute a pixel level correspondence between the contact point you see at training time and also all the points on the target object. So this will give you a heat map where the highlighted area corresponds to pixels or object locations. It had like with similar local geometry as the contact point happened in the training time. And of course, here this particular heat map is very noisy because we're just using a very general purpose visual recognition model. So here the king said we can use that as a guidance for a model-based planning algorithm to finally solve the task. So the overall pipeline is we're extracting this heat map, we are sampling contact points based on the heat map we extracted. And then we use that to initialize actual contact-based motion planner, trying to simulate what will happen if you do all those actions and find a path to the original problem. And then this allows you to doing one-shot learning and one-shot generalization to like hang a novel object onto a novel object. And here our model only rely on, first of all, a 3D reconstruction model that can take camera images and reconstruct the object 3D shape. And second of all, a general purpose physical simulator like Mujoko to simulate what will happen if you move your robot and then how you want to hand the object. And this can be applied, to all different kinds of objects, including different kind of mugs and different kind of like a measuring cup. And to stress test our approach, we also show that this generalization to different kind of alphabetical shapes, and you want to hand them onto the mug tree. And here you can see that the system is able to smartly pick different kind of grasping poses depending on the shape of the target object, and then different hanging position so that the object being stable on the target mug tree. And this can be reflected as well in some quantitative tasks. Like, we measure the success rate of hanging a bunch of objects we have in the lab. We compared our approach with, direct policy learning from one single example. And, of course, it's probably not surprising this approach actually will not work because you only have one single example. You can also augment the policy learning algorithm with the visual correspondence map we had before as a fair comparison using the same, Dino V2 feature. And you get something better, like a 24% of your generalization. And our approach is able to successfully hang, 93% of all the objects in our physical tests in our lab. So in this part, I've described, this, constraint optimization framework with, mostly just like human-defined kind of constraint, which is, how to make contacts. And this can be also extended into, learned constraints. For example, suppose that our task is to lift the handle of a coffee machine and to operate that. And here what you need to learn is, what is the constraint, what is the motion constraints of the handle, relative to the body of the coffee machine because of all those like linkage structure. So here what we can do, you can learn constraints over the handling opening motions and then generalize that to different kind of objects and backgrounds. In this paper, what we're doing is we're still taking visual pre-trained feature, Dino V2, and here we are using slightly more data, like a 10 human demonstration instead of just one, and then training a model to learn the constraints of the handle opening motion. And then compose that with all the other physical constraints like collision avoidance or robot trajectory or robot IK, all those kind of things, to achieve the generalization to all different kind of objects with different backgrounds objects and so on. So to summarize for this part, for the second part, I've described an approach for doing one-shot learning or very few shot learning of generalizable actions. And the advantage is we can learn from them and generalize to novel objects and possibly novel background objects, and then for different situations. And then the principle here is we're composing some visual representations for visual level generalization and some physics models, like how to solve collision avoidance, how to solve for the robot IK under this general neuro-symbolic constraint optimization framework. Before I end, I want to give you some extension to some of the the recent work that we extend to the previous work, trying to extend that to the composition of such kind of learned generalizable actions. And this also refers back to the ABC pickup challenge we mentioned at the beginning of the talk. So in this work, we are training the robot with one single demonstration each for how to use two sticks to rotate an object on the table, to push an object on the table, and to lift up an object. And then all those demonstrations are given on the alphabetical shape R. And our system, after doing this kind of learning, because of its compositionality and a strong generalization, now it can generalize these learned concepts to different kind of objects you have never seen before, in this case, like a D, and to compose them sequentially to solve the task. Because in this case, your system need to actually make decisions about if you want to rotate it, by how much degree you want to rotate. If you want to push, by how much distance. And when you're lifting it up, what are the contact points there? And all those kind of things are resolved using a single unified constraint optimization framework to have such kind of strong generalization. So of course, for now, the task we're demonstrating here is still relatively short horizon, at a time scale of probably like a 30 seconds to a minute. So our hope is when it extends such kind of framework to do long horizon planning. That is, actually having a robot that can execute tasks that spans over minutes or even hours, hopefully. So in the last part of the talk, I'm going to mention my work on learning to make long horizon plans. We're going to first describe what kind of data we have. We assume that we have some human collected robot trajectories and some language generations of solving tasks in a particular domain. In this case, like the kitchen example. So assume that the demonstration is collected by the human teleoperator, and it is segmented and annotated with language generations, such as, from this time step to that time step, the robot is trying to grasp the dish soap. In the next step, we're going to pour the dish soap onto the plate, and then we're going to place the dish soap back onto the counter, and so on. And our goal is learning from a limited number of demonstrations like this, try to make long horizon plans with generalization to unseen states and goals. What do I mean by that is, you hope the system can generalize to different initial states. In this particular case, a person probably is trying to wash a plate under the raining water, but because they need a phone call, so they actually left the faucet open, but does not have the dish soap on the plate yet. So in this case, the robot, given the goal of put a clean plate on the rack, has to reason about, okay, there's currently no dish soap on the plate, but the faucet has already turned on. So what I need to do is I'm gonna keep the faucet turning on, but pour some dish soap onto the plate and then try to pick up from the kitchen counter, and try to rinse it in the running water. This also allows you to be more adaptive to partial observations. Here, the robot is receiving the goal of put the plate onto the rack and then clean the counter. And after the execution of the first few steps of the computed plan, originally, the robot only sees there's a plate on the counter. The robot will recognize, oh, there are actually some dirty pieces on the table. So the robot needs to continue to adapt and recognize what are the state changes that you see, and then how to make new plans adaptive to it. So the way we're going to do that is we're going to use language to help us make sense of a long horizon plan demonstrated by the human. So we're building a learning algorithm that give the demonstration and also the language generation being able to reconstruct the neuro-symbolic concepts, including the state features, like what are the states that matters in the target domain, and what are the actions in the domain, and what are the preconditions and what are the effects. And of course, learning how to recognize all those features and how to perform each individual actions. Before I jump into the learning algorithm, I'm going to first, give you some idea about, suppose I already have such kind of representation, what can we do with it? The way that we're going to use that is we do planning with the learned representation. We use the state feature extraction that we learned, to recognize all the objects and all their states, such as, the first object is a plate, it does not have soap on it, the faucet is currently not turned on in this particular case, and then the object is not on the edge. And then this gives you the state representation for the initial state. With your action model, what you can do is you can do the effect prediction of if you take an action, what will happen. Like, if you post soap, then this will change the has soap state of the first object. And this gives you the abstract state prediction of S1 after doing the action pouring soap. And you can do that for different kind of actions. And then also do that recursively. And then the final goal can be represented as a logical formula over the final state, such as there exists X and Y, such as X is a plate, Y is a rack, and also X is clean, and X is on top of Y. Therefore, what you can do is you can search using the learned effect prediction model and translating the original goal into the logical formula, and so that you can find a path from the initial state to a target state, satisfying where the final state satisfies the goal. So this is like a short overview of what a planning algorithm would look like. Now let's talk about the learning. So learning has 3 stages, which leverage a lot of ideas we've seen in the past of this talk. The first step is giving the language narrations and some annotations. We're gonna ask a large language model to do code generation, generating what are the features that are relevant in this task, and what are the actions, and what are the preconditions and goals. And here, the large language model is leveraging its pre-trained knowledge about generally how to solve a task in the semantic space to identify features to track and the precondition effects for different actions. The second step is we're going to do the learning for the action bodies. We're exactly using kind of a very similar framework as the one we described in the second part of the talk, like learning the constraint model and compose that with robot, IK solving and motion planners. Here, what you're learning is essentially learning grasping poses, placement poses, and maybe trajectories of the to manipulate the faucet, for example. The remaining part is all those state feature symbols, like has soap and on edge, now still remain uninterpreted to the robot. Like they still do not know how to recognize if this is a plate or if the faucet is turned on or not. To do that kind of learning, what we're going to do is we're going to learn the state features and the transitions. Basically, how to ground those state feature symbols like has soap or clean. And you will see that this is actually exactly the same learning problem as our first example on visual question answering, but only extended with a temporal axis. So let's take this particular effect prediction model as an example. Like if there's original soap on the target object, then after doing this action, the object will be cleaned. To remind you how to do this, you do the object recognition and then you extract the object features. Here, has soap is a neural network that takes the visual representation of the object in the first frame and then predict whether it has soap on it or not. It outputs some like a probabilistic value. And then also the clean classifier is a classifier taking in the visual feature of the object from the after state of this action. And then can compute if this statement, if then statement is true or false. The way that we're going to do that is the probability that if A then B is true equals to the probability that the statement B is true or A is false. And then since this is a demonstration trajectory, so you actually know this statement should hold true. So you can say the ground truth answer to this statement is true. Is actually it actually complies with the before and after state. Now we can do gradient update for the has soap classifier and also the cleans classifier. So after having those neuro-symbolic concepts, another advantage that we have we've shown in this framework is now you can use general purpose planning algorithms to find robot actions. And actually, furthermore, based on the neuro-symbolic concept representation, you can do faster planning. Instead of like doing just complete enumerative search of all possible sequences of actions to take, by automatically compute approximated value functions based on the compositional structure of those actions. Like this action is a prerequisite for another action based on the precondition action and effect definition. And previously, this is only known for totally discrete domains in classical AI planning literature, and we extended those methods to continuous value states. So we also compare our methods with state-of-the-art approach for solving such kind of long horizon manipulation tasks. In this case, comparing with vision language models. The parameter based on compared with is called the robot Villa, which is based on GPT-4V. And then its overall framework is, given the state represented as an image and given a goal represented an action, you have a VLM output and language command, which used as the input to a controller, which output the robot action. The challenges here for those kind of approach is, of course, memorizing all the training trajectory will not work because we're going to test it on different kind of scenarios. And error will accumulate if you have a long horizon manipulation task. And you also need to understand geometric constraints, like this object is blocking you, that object needs to be on the edge so that you can pick it up. So we tested it on a few domains. This is one of them called the boiling water domain, where it's a long horizon task set up in the physical world with some small objects, like you want to place the kettle into the sink, move the faucet head away and towards the sink, turn on and off the faucet to get some water, possibly place some obstacle currently on the stove to the table, and then put a kettle on the sink, put a kettle onto the stove manually, and then to heat it up. Our approach is based on having the state abstraction, having a planner, given the goal, output the action commands, and then using the controller to solve the task. So we train both systems using the same kind of data, which is based on one training situation, and then generalized to 6 different things initial states. Like object could be missing from one location, or the initial state of the faucet could be at a different state as you've seen at a training time. And then if you test the overall success rate, you will find that those vision language model actually gives you only across the test in our lab. It never succeeds in solving any one of those generalization tests. Although if you ask it to follow the original sequence of actions, it can do some reasonably job. By contrast, our model is able to achieve 6 out of 6 success rate. And then recently we're extending this approach to vision language model based segmentation and augmentation. Basically, previously we still rely on human to annotate what is happening in the trajectory. But now if you have a video understanding model, you can use that to help you to enable the segmentation and what is happening there. And here the training data is just 10 demonstration about how to rinse one plate and place onto the dish rack. And our test goal is to wash all plates. And here, the robot is making a decision about, in which order you want to pick up all these objects, because in this case, because there's some geometric constraint between the relative pose of these 2 plates, you have to make sure you want to pick up the one that's closer to you first, right? And also, the system is, learning all those, executing all those learned skills to rinse the plate and then, successfully place them onto the dish rack. So to summarize, I have described this approach for doing neuro-symbolic concept learning, for how you can use that for reasoning and for planning to achieve very data efficient learning, including how you can learn the visual concepts from 10% of data or even less. And learning actions from a single or very few examples, like the final one, we're learning this bimanual skill using only 10 demonstrations for one plate and generalized to all different kinds of objects. With strong generalization to complete unseen objects at the individual skill level, and also generalizing different kind of initial states and novel goals by using planning. So before I end, I want to quickly mention what do I think is the future for neuro-symbolic concept learning, reasoning, and planning. So nowadays, a lot of the people are talking about this idea, building foundation models for reasoning or for embodied reasoning for planning. The approach I described in this talk illustrates a way to build a compositional foundation model for reasoning and planning purposes. So in this talk, I started with some features, state features, and some action models, and each one of them associated some neural networks for doing the recognition work. But they are very specific to a particular domain. Like this one is just for classifying whether an object has soap on it or not, or this is classify whether it's dirty or not. So the issue with this is, you have like different tasks and you would need different abstractions. So at the end, you end up having a bunch of, maybe a million of different state feature and action models and so on. And this will hurt both your learning and planning. If you want to scale this up, what you can imagine is you can have a model generator to replace an actual, code-defined library of state features and action models. You want to have, general purpose, visual models and robot models for doing object detection work, to doing relational extraction work, to predict the physical dynamics, or to find, to find values that satisfy certain kind of constraints. So for example, the model generator should be able to take as input the context, including, the initial scene and maybe some human language instructions, being able to output what are the state features and action models that are relevant in this particular task. You can imagine this is a perfect job for, vision language models or, large language models or, multimodal models that does some kind of like a code generation. And what we actually do not have is some kind of models that can do general purpose visual recognition and embodied, constraint satisfaction solving or dynamics prediction work. Those models look like, you have some sensory input, you have some concepts you want to recognize or a constraint you want to find values to satisfy. And it can output different kinds of things like a Boolean for recognition task, like a pose for a generative task, like a grasping pose, or like a robot trajectory, or maybe predicting what are the forces you need to do. So right now we arguably have, relatively good model for just detecting object states and then, recognizing some kind of relationships, although not perfectly. But on the, on the robotic side, how to find values, satisfy certain, geometric constraints, or, how to predict physical dynamics in a general purpose case is still, largely unsolved. And this gives us a lot of, possibilities of, building novel paradigm for training and composing such kind of large model trained from diverse kind of data, including robot data, but also all kinds of other data, like video data or images, even just like image data. So another thing that is, kind of missing is the capability to do continual learning. That is, currently most of the things we're doing is still relying on human collected data, like we're annotating them. So the hope is that we can start from some basic compositional foundation models, using them to do reasoning, planning, and actually explore in the physical world to get new competence, like for example, like solving a new task. And then those kind of the experiences associated with the new competence will naturally serve as the data for learning stronger foundation models that can be used as the basis for the next iteration of learning. So this is, in analogy to how human babies learn. We start with some core understanding of the physical world, like understanding their objects and their space, and there are other agents in the world, and then some basic understanding of logic and the numbers. And then we ground language on top of that, doing language acquisition, ground all those kind of object features and actions on language terms. And finally, to really achieve, the human level intelligence, what you need is self-exploratory learning. That is, you want to think about what are the novel goals you want to achieve, what are the new skills, and what are the, new relations or learning novel human preferences you've never seen before, being explicitly taught in your language state. So with all that, I've, in this talk, I'm describing this general purpose framework for learning, reasoning, and planning with neuro-symbolic concept with a focus on robotics manipulation tasks. And I argue this is a new bet for building generally intelligent agents that really bridges two things. The first one is the understanding of intelligence, like understanding the physical environment, understanding the sparsity structure of it, understanding the computational complexity theory behind it. And how we build intelligence, like actually ground all those high-level theoretical insights and intuitive insights into actual algorithms using this neuro-symbolic concept framework. And this is a new bet for general intelligence, in contrast to just blindly scale up the data we have, and then hopefully one day this system will generalize. So this comes to the end of my talk. With that, I want to acknowledge all the funding agencies, my advisors and collaborators, and also some of the mentees that I supervised over the past few years, which contributes to the work mentioned in this work. So with all that, I am happy to take questions.
Right. Thanks a lot for the talk. We'll take first questions around here and see if there is something like that. All right. Questions? Good. Some people online. Have any question? Let me try. Oh, wow, so it was pretty clear, it seems. Yeah, let me see. I made some notes. I actually have a couple of questions here.
I have one. How do you define the constraints? Like, how do you know which constraints are there? And if you change the application or a task, do you have to like keep adding a list of constraints based on the task?
Yeah, so basically for the robotics case, some of the constraints you can think about them as intrinsic constraints, such as basically as long as you have this robot to operate in the physical world, is to have some constraints like some velocity constraints, some force constraint, the robot kinematic itself forms the kinematic constraints, right? And then there are also kind of constraints about how you execute a task, like your for example, your constraints on the target relative pose between two objects, or the target object states. And then basically what you can think about is all those kind of constraints can be learned from different sources. Some of them could be manually defined in the case of kinematics. As long as you have the URDF file, the robot definition of it, then you can directly compute it. And then for other constraints like what is the stable grasping pose on the mug, you need to learn them from data. I'm not sure if this is the question you're asking.
That answers it. But like,
Okay.
What do you think are the challenges of learning the constraints from data? Or did you try something like use some demonstrations or interventions to like actually learn the constraints?
Yeah. One of the constraints that we actually constantly see, in this kind of framework is usually when you have a demonstration, the trajectory is a demonstration of how to satisfy multiple constraints at the same time, right? So for example, if you're moving a mug, in a certain way, right? No one is telling you the particular trajectory is totally explained in the sense of, this is because I want to keep the mug upright, or is it because some of my kinematic constraints so that I can only hold the cup upright, right? So there's kind of like ambiguity in your learning. This is very similar to inverse reinforcement learning, where you have a trajectory and you want to use a reward to interpret that, to make sense of it, and then you have the ambiguity problem there. So therefore, the proposed idea we have in this paper is, or in this framework is, first of all, you have some language, data, or you think about like a large language model to help you to identify what are the set of constraints. Just talk about their names, and then what is the factorization of those constraints. Like this constraint only depends on the robot. That constraint depends on the object states only. For example, the mug needs to stay upright, or I'm moving it. And then you need to, but even after that, even knowing the the structure of all those constraints, think about like the sets, you still need to have a learning algorithm that can isolate or learning a generalizable version for individual constraints. In the past, we're primarily relying on just gradient descent, and then there's nothing fancy there. But one interesting approach is you try to connect some of the inverse reinforcement learning work. For example, doing max entropy learning, think about like each constraint you should explain. You want to hope that the trajectory can explain has the maximum entropy. This as additional regularization for the constraint learning, and then also this also has some connection to constraint learning or control barrier function learning in the control theory work. And then I think at the end, all those kind of things need to be kind of unified, and then we need to think about what are the pros and cons of them. But the idea here is the constraint satisfaction framework is really, really general and allows you to have all the kind of data efficiency and generalization you hope.
Right. Yeah, that answers. Thanks.
Yeah. Miguel here again, thanks. I have a quick question about the idea of memory. Like all the examples that you show have like a fixed camera view with all the object filters within the scene, right? But like, what would happen in the scenario where you actually have to interact for a very long time with an object that you need to place outside the camera view? Like, have you do anything about like put the cup in the kitchen now, go to a living room, bring some coffee afterwards? That kind of idea, I guess. Have you thought about it? Or...
Yeah, that's a great question. So and that's a great catch. So in short, we didn't do that in all the work that we mentioned. I think this point, the way that I interpret this is one more thing that's missing in the framework is how we think about memory. That is, how we can maintain a memory over space and over, object states and over, maybe human preferences over time. And then in this particular case, you were mentioning a naive solution is you augment the existing system with some kind of like a SLAM system or object-centric SLAM system that can keep track of object states and so on. The issue with that is if you just represent everything as, for example, just videos or like a large scale scene point clouds, the reason about them is still going to be very, very slow. So I think one interesting idea is to think about how the neuro-symbolic concept framework, which is the kind of idea is you factorize your state representation into different states, different concepts. How that kind of factorization could also bring advantage into the memory system. Like, for example, an intuition is that, you don't have to maintain a whole joint distribution of the entire scene point cloud and all the, the pixel values, right? But what you need is just to maintain distributions of concept values that you care about for solving the task. So that is an interesting extension that we hope to work on.
That makes sense. Yeah, that's a definitely interesting idea.
Yeah.
Right. I think that's it. Yeah, there's a more questions. So thanks a lot for giving the talk again. Please keep in touch. And best of luck with your next position.
Yeah, thank you very much for having me. And then thanks everyone for listening and then asking those great questions. Nice to meet everyone. Yeah.
Our pleasure. Take care. Bye-bye. Ciao.
Okay, bye-bye.